The constraint motion like this always confuse us, that where to begin? Let us see problem of the day. Two blocks of mass m are hanging at either end of a string. And string runs over to fixed pulleys, and its middle section joined together at a third mass, capital M, hanging in between. The middle section make an angle theta with the vertical. Now, if both end are moving down with the speed u, with what velocity does mass m go upward? Let's unfold the solution of the pulley constraints problem once and for all. First, let us understand what constraint motion actually means. In simple, layman terms, we can say constraint motion is motion where two or more bodies are interconnected. So what does that really look like? Let's take an example. Here, two bodies, M1 and M2, are connected by an inextensible string. Inextensible simply means the length of the string is constant. And the string is taut, so there's no slack anywhere. Now, if M1 moves by a distance x1, and M2 moves by a distance x2, then it's obvious that x1 must be equal to x2, because the string length never changes. And this means the velocity of both objects will also be the same. Let's take this idea one step further with another situation. This time, the two masses are connected to each other over a pulley. Again, let's assume the string is inextensible, with a total length, capital L. Let the position of each mass be at a distance, L1 and L2, from the pulley. So the total length of the rope can be written as L1 plus L2. Now suppose M1 moves down by a distance x1, and M2 moves up by a distance x2. Then the new lengths become L1 plus x1, and L2 minus x2. So the total length of the rope in this new condition is L1 plus x1 plus L2 minus x2. Now, if we differentiate this equation with respect to time, we get V1 minus V2 equals 0, which proves V1 is equal to V2. Now let's apply this exact same concept of constant length to the problem given. Let's call the string length of each section L1, L2, L3, and L4. Now suppose both the end masses move down by x1 and x4. And the mass in the middle of the rope moves up by x2 and x3. So the new total length of the rope can be written as L1 plus x1 plus L2 minus x2 plus L3 minus x3 plus L4 plus x4. Now, differentiating this entire equation, we get V1 minus V2 minus V3 plus V4 equals 0. Now, since V1 and V4 are both given as u, we can rewrite this as 2u. And since the mass m in the middle is moving up with velocity v at an angle, the component of v along V2 and V3 can be written as v cos theta. So overall, we get 2u equals to v cos theta, which finally gives us v equals u by cos theta. And that's it. I hope this explanation has cleared your concept of constant length in constraint motion problems. We'll be posting more problems like this on our Telegram and YouTube channel, so you can practice more. If you liked our approach, do give us a thumbs up and hit that subscribe button. And don't forget to recommend the channel to your friends. We are Numericals Studio, your inevitable partner for engineering and medical entrance preparation.